Mr. Chairman, ladies and gentlemen, good morning. It's very great pleasure indeed for me to be able to attend this meeting. My name is Jing from Southeast University of China. The topic of my report is rolling bearing fault diagnosis and prediction based on VMD-CWT and MobileNet. Please allow me to introduce myself first. My name is Jing, and my major is thermal energy and power engineering. I was mainly engaged in the research related to the mechanism of unit equipment failure and intelligent diagnosis. To be specific, in the aspect of signal analysis and processing, I engaged in signal decomposition, signal denouncing, vibration analysis, acoustic emission technology, and other aspects. Data mining includes feature extraction, anomaly detection, fault diagnosis, artificial intelligence algorithm, health status evaluation, remaining life prediction, and other related aspects. I will elaborate my article from the following aspects. Okay, one, introduction. Wind power as a kind of clean energy accounts for an increasing proportion of global energy. By 2019, the total installed capacity of the world has reached 60 megawatts and continues to rise. However, due to poor operating environment and the lack of operation, the transmission system failure rate of wind turbines is high and the operation cost is greatly increased. In recent years, a large number of units will exceed the warranty period into the outbreak of failure period. So strengthening the wind turbine operations state monitoring, take measures to avoid major equipment failures timely has become an urgent problem to be solved all over the world. Next, I will briefly describe the algorithm used in this article. In the aspect of signal processing, due to the high ambient noise of rolling bearing in engineering environment, this paper used the VMD to denoise the signal firstly. In the fault diagnosis of rolling bearing, the appearance of periodic path components often indicates that the occurrence of faults. Wavelet transform is the convolution operation between the original signal and the wavelet function, which actually measures the similarity degree between the signal and the wavelet function. In this paper, CWT is choosing to carry out time frequency transformation of the signal. CNN has been widely used in the field of computer vision and industry for its excellent image classification effect. However, with the improvement of model classification accuracy, the depths and the complexity of the model are increasing. A small increase in model precision brings about a huge increase in model parameters. However, in real application sensors, especially in the transmission system of a wind turbine, if a mechanical failure is not handled in time, it will bring serious consequences. Fault diagnosis requires strong real-time, low latency, and faster response. convolutional neural network has a large memory requirement, which makes it impossible to run on mobile device and embedded devices. MobileNet is a lightweight CNN network proposed by Google. Compared with the traditional convolutional neural network, it greatly reduces the model parameters and the calculation amount under the premise of slightly lower accuracy. The core of the model is depth-wise convolution, which decomposition standard convolution into depth-wise convolution and point-wise convolution. It can be seen from figure that in traditional convolution, China of convolution corner is equal to input corner, input China, and output China is equal to the number of convolution corner. And in DW convolution, China of the convolution corner is equal to 1. The input China is equal to the number of convolution cores is equal to the output China. So theoretically, the calculation amount of ordinary convolution is about 8 to 9 times that of DW plus PW convolution. MobileNet V2 uses the inverted residual structure as shown in figure. The inverted structure increases the dimensionality of the input matrix by 1 multiplied by 1 convolution, and then uses a 3 multiplied by 3 DW convolution corner for convolution, and then uses a 1 multiplied by 1 convolution corner for dimensionalities reduction. The first 2 layers of the inverted structure uses ReLU 6 as the activation function. In the last convolutional layer, a linear activation function is used instead of the ReLU activation function to avoid causing a large loss of low-dimensional future information. The figure is the main flow chart of MobileNet V2. In order to prove the effectiveness of the CWT, the simulation of rolling bearing vibration signals were used to verify the result. A simulation signal with AM and FM characters is constructed. Time frequency analysis based on PWVD and CWT are carried out for the simulation signal respectively. Time frequency analysis based on PWVD and continuous wavelet was carried out respectively for the simulation signals, as shown in the figure. The time frequency diagram is obtained, in which figure A is the time frequency diagram of wavelet continuous transformation. It can clearly observe the frequency of component that always exists at 120, and the frequency component that is slightly around the 20. Figure B is the PWVD time frequency diagram, and we can see the 120 and 20 frequency components, but they are not clear. In contrast, CWT time frequency diagram has higher time frequency resolution and can clearly present each frequency component. In this paper, the VMD algorithm is used to extract the signal features. The CWT was used to extract the time frequency features. After the data was enhanced, the MobileNet network was trained in order to accelerate the convergence speed. In this paper, transfer loading was aided in the network training process, and the weights of the first several layers, which are pretrained on other data sets, are transferred to the corresponding network. The dataset of rolling bearing from Case Western Reserve University is used. This is the physical diagram and the experimental platform. It shows the waveforms of 4 vibration signals of rolling bearings under the condition of 0.007 inch crack. In order to improve the recognition rate of time frequency images, VMD feature extraction was first carried out on the signals. It is the comparison of time frequency images before and after VMD feature extraction and normal and rolling body fault conditions. It is clear. It is more clear. It shows the error convergence curve of the MobileNet network in the training process. As can be seen from the figure, the loss value of the model turns to 0 and remains stable when the iteration reaches the set time. At this point, the model has been trained to the convergence state. As can be seen from the figure, the test set has a recognition rate of 90%. In order to further prove the effectiveness of the method presented in this paper, time frequency images without VMD presence are used to train the MobileNet network, and the error convergence curve is shown in it. It can be seen from the figure that the recognition rate of the test set only reaches to 60%, which proves the advantage of the method in this paper. From what has been discussed above, we may arrive at the following conclusion. After the extraction of fault features by VMD, the fault features of time frequency images are more obvious. The time frequency focusing of time frequency images is better. The impact is more obvious. 2. The comparative experiment shows that the fault classification accuracy of the MobileNet network only is 60%, and the fault classification accuracy of the proposed method is 90%, which is a great improvement. 3. The comparison of CNN experiment shows that the proposed method can reduce the network trailing time with a small reduction of accuracy. That's all. Thank you for your attention.